All right, good. Back to screen share. Thank you for reminding me, because I probably would have gone on for quite some time without doing that. Let's see here. Okay, so I hope we're finally set up for tonight. All right, so a pure state is one in which the statistical sum contains only a single term with 100% probability. So if there exists such a psi that rho is equal to that, then what we have is we have what we call a pure state. We say that psi is a pure state. So that's the definition of a pure state. And otherwise, if that's not true, then we say we have a mixed state, like this. So pure states correspond to mostly what you probably did in your first course in quantum mechanics. You've got a wave. If you have a pure state, you see you have a wave function. It's this state, the wave function of that state psi. If you have a mixed state, then there is no wave function. At least there's no single wave function. You could put it that way. In any case, it's clear that what you've done in most of probably your first course in quantum mechanics was mostly working with pure states. However, and that's normally the case that's also going to be the case in this course too, but in real—
Sorry.
Yes.
We say that the ket is the pure state, or that the system is the pure state?
We say the system is in a pure state if the density operator can be written this way. And what that means is that there's one state with 100% probability, one wave function psi. Okay, so that's the case.
Okay.
That it's a pure state. If this cannot be done, then we call it a mixed state. So, but what I was starting to say is that mixed states are the norm in real experiments. So keep that in mind, even though they're going to be a minority of this course. Okay, so that's the definition of a mixed state. Now, if you're on top of what I've been saying here, you'll recognize that I've been giving you kind of a runaround, because I defined the density operator in terms of a statistical mixture of state vectors, which is to say pure states. And having done that, I'm now defining a pure state as a special case of a density operator. And so this logically is not satisfactory, and it's kind of circular reasoning. I'm going to fix this in a minute and make it logically correct and coherent. But I did it this way anyway, because you have experience in calculating probabilities using wave functions. And so I hope that this presentation at least gives you an idea of what we mean here by a mixed state, in terms of, it's obviously a mixture of some kind of classical probabilities that are determined by those probabilities f sub I, combined with the quantum probabilities or statistics that's inherent in the measurement process of wave functions. This is the idea of, roughly speaking, of the density operator. All right. Now, let's before we fix up the logical deficiencies of this presentation, let's proceed to work out some of the properties of density operators. So these are pretty easy to write down. And in writing down these properties, I'll rely on the discrete form of the density operator. That's a sum on I of probabilities fi times outer product psi I with itself, psi I. Let's see, like this. Right, good. So the first property is that rho is equal to rho dagger, which is to say that the density operator is Hermitian. That's kind of obvious from looking at it, because the outer product goes into itself under Hermitian conjugation, and the f sub i's are real. The second property is that rho is non-negative definite. And to say that an operator is non-negative definite, I'll say what that means down here. What that means is that if I take an arbitrary state phi and I sandwich it around rho like this, that the result is greater than or equal to 0 for all such states phi. That's what you mean to say that it's non-negative definite. And the reason this is true is because if I take this sandwiching and use this form here for the rho, you see what I get is a sum on I of probabilities fi, and then I get the scalar product of psi with phi I times the scalar product psi I with phi. And that's the same thing as the sum on I of probabilities fi times the magnitude of the scalar product phi with psi I quantity squared. And now you can see that what's being summed over here are strictly non-negative quantities, a probability in a square of something. So this has to always be greater than or equal to 0. And that's a proof of the fact that rho is non-negative definite. It's also Hermitian. And the third property is that the trace of rho is equal to 1. And that follows quite easily because the trace of the outer product, the trace of any outer product is the same as the inner product. And I'm assuming here that these size are normalized, so the inner product is 1. So the trace of rho is just the sum of I of the f sub i's, which is equal to 1 because those are probabilities. So what you can see is that this third property, trace of rho is equal to 1, is really a normalization condition on density operators, and it says that the total probability adds up to 1. All right, so these are the three main properties of density operators derived from our quote unquote definition that we have up there.
Professor,
Yes.
I'm just wondering about the density operator. When we call it an operator and we say it's Hermitian, then it sounds like it should be some sort of observable. But I'm not sure intuitively what that means if it's an operator.
Well, it is an operator, and we know that observables are associated with Hermitian operators. In fact, rho is a Hermitian operator. Rho is not an observable in the usual sense of observables like Hamiltonians, corresponding to measuring energies and so on. What rho does is it gives you the statistics of measurement. In other words, rho represents the state of the system. It depends on the system, in other words. It depends on the state of the system. The system here means an ensemble of systems, and because we're talking about being able to make repetitive measurements and gathering statistics, this is what quantum mechanics predicts. I think your question may become more clear as we go on. It is an operator, but it's not the usual type of operators that are associated with physical observables like energy and angular momentum. It's obviously an operator because it's a sum of outer products, which are operators. All right. Now, these are the properties of rho. Now, one of the things we've done so far is to say a lot about rho, but I haven't given you any examples yet. So let's do some examples. I think a good place to do that is to go back to the Gedanken experiments that we talked about in a previous lecture. So I've recalled some of the diagrams here. You may recall we talked about a Gedanken experiment in which we had a Stern-Gerlach apparatus, so that we've got a silver beam coming from an oven. This middle thing here is a collimator to create a beam that comes out of an oven. We then measure the component of the spin in the direction in hat. That's what the S of in hat means. And we get either answers, plus or minus h bar over 2. The answer with a plus value, we pass on to a second observer. These are observers 1 and 2, who then is able to make measurements of some observable. Now, after the measurement of S sub n hat, based on the assumption that the Hilbert space is two-dimensional, which is what we work through in that analysis of the Stern-Gerlach apparatus, once that measurement has been made, the system is, of course, projected onto the eigenspace of that operator, which by our assumptions is a one-dimensional space. And so that projection produces a vector lying in a definite ray, and therefore a definite state. And so a definite pure state, as a matter of fact. So along this line here, the beam, which is being fed into the second observer's measurement apparatus, is in a pure state. And in fact, it's a silver atom that's been polarized in the in hat direction. So that's what's being fed to the second observer. Now, we considered this is a real Gedanken experiment now. We considered in an earlier lecture what would happen if the first observer oriented the measurement apparatus on seeing a silver atom approaching, oriented the measurement apparatus in a direction in hat, which was chosen randomly over the surface of the sphere. What that would mean is that in a certain sense, the second observer is receiving silver atoms that are polarized. They're polarized in a definite direction in hat, but that in hat, let's say, is only known to the first observer, who does not share that information with the second observer. So they're polarized in a random direction. So then the second observer can make measurements. We also made the argument, which was not proven, but it was just a physical plausibility, that this ensemble, which is received by the second observer in this manner, is physically equivalent to the beam that's received directly from the oven. So that observer A, or second observer here, would be unable to tell if we actually bypassed the first apparatus with its randomized direction of polarization and just brought the beam directly in from the oven. Okay, we talked about that in the previous lecture. Well, in any case, it's straightforward to compute the density operator of the beam which is received by the second observer, because what it is its state vectors, which are polarized in a definite direction, but that definite direction is randomly chosen, so it has to be randomly averaged over the surface of the sphere. That means then the density operator rho is given by the average over solid angles. I'll write it as integral of d omega over 4 pi. This is an example, by the way, of a continuum, a distribution of state vectors.
So in this example, are we every single time a particle passes through, we're changing the direction that we're choosing, or
that's the idea. Yeah. Suppose you could do that.
Okay.
So think about it this way: is that second observer is receiving silver atoms that are polarized, but they're polarized in a random direction. All right. So then the density operator describing that statistical ensemble is one where you have the n hat here refers to the n hat. The n hat is just another way of writing the spherical angles of the direction of polarization. So the outer product n hat averaged over the surface of the sphere. That's what the density operator is by the definition. Okay. Well, now in two component spinor form, I displayed for you earlier what the state vector is for a spinor polarized in the direction theta and phi. It's given by these trig formulas here, and that's supposed to be a cosine there. I'll write it again better. That's a cosine of theta over 2, and this is sine theta over 2. So we can do this integral here this way. This is just a simple calculation. For the ket factor, we write this as a column vector, column spinor. It's e to the minus I phi over 2 times cosine theta over 2. I'm really just copying this above. And the lower component is e to the plus I phi over 2 times sine theta over 2. And then we multiply this times a rho spinor, which is the same as this bra here. This becomes e to the plus I phi over 2 times cosine theta over 2 in the first slot. And then e to the minus I phi over 2 times sine theta over 2 in the second slot. I didn't leave myself enough room to write that very well, but this is what you have for this outer product. Now multiplying this column spinor times this row spinor gives us a 2x2 matrix. And the upper left-hand corner is cosine squared theta over 2. The lower right-hand corner is sine squared theta over 2. The off-diagonal element up above is e to the minus I phi times sine theta over 2 cosine theta over 2. You can just do the multiplication. And then down here in this lower left-hand corner, it's what's in the upper left-hand corner complex conjugated, as it has to be because rho is a Hermitian matrix now. All right, so this is the outer product, and we need to average it to get the density operator. Well, the average of the cosine squared of the sine squared is 1/2. So that's what you get on the diagonals when you carry out the average. The average of the off-diagonal elements is 0, as you can see, because averaging over the azimuthal angle phi alone, never mind the theta dependence, the phi alone dependence is going to average to 0. So we get zeros like this. This then is a calculation of a specific density operator of representing the statistics of the being being fed to our second observer here. And if our physical reasoning was correct that I explained in an earlier lecture, that's also the density operator representing the quantum state of the beam coming from the oven. It's one in which the polarization is in a random direction. All right.
Professor?
Yes.
Is the reason why we have no off-diagonal terms because n was a pure state?
No, it's because, because you do have off-diagonal terms in the outer product n. Here they are. But the off-diagonal terms averaged to 0 when I averaged over the surface of the sphere.
Right. I guess what I'm saying, yeah, I see that you have off-diagonal terms before you compute the integral, but then after you're left with,
with a different ensemble, I would end up with off-diagonal terms.
Okay, I guess my question is then, like, what is the interpretation of the off-diagonal terms as?
It depends on the basis, because you see, a matrix, whether a matrix has off-diagonal terms or not depends on the basis.
Right, right.
Okay. But that's a good question, and this is an issue that comes up again and later on. All right. So anyway, this is the rho then for the thermal beam coming out of the oven, or from this Gedanken experiment. Now allow me to change this Gedanken experiment in a different way. Let's suppose observer 1, instead of randomly choosing to polarize the silver atoms in a random direction on the surface of the sphere, Suppose observer one, he or she, decides to polarize it in only two possible ways, either at the North Pole or the South Pole, flips a coin, decides which of the two it's going to be, orients quickly the Stern-Gerlach apparatus either in those two directions, and then if the silver atom is polarized in that direction, passes it on to the second observer. So now the second observer is receiving a different ensemble, one that consists of silver atoms polarized in only two choices of directions, plus and minus z hat, with equal probabilities. And so now, what is the density operator corresponding to that ensemble? Well, that's easy to work out. I'll find a place for it here. Let me just write it down here. By our discrete formula, it's the probability of 1/2 of the thing being in the spin up direction. So I have to put the outer product of up with itself, plus the probability of being in the spin down direction, probability of 1/2 with the outer product minus for that being in that polarization. And if I take that density operator and I write it in a matrix form, look what it turns into. It's 1/2, 1/2 on the diagonals and zeros in the off diagonals, like that. So it turns into exactly the same density operator as you have if you polarize the silver atoms in a uniform manner over the surface of the sphere. All right. Now, I like to say that the density operator contains the physics, all the physics, and nothing but the physics. And what that means is that in the first place, it contains all the physics because, as I explained earlier, the outcome of any experiment you can do is given by, if you know the density operator, you can predict the outcome of any experiment you can do by this magical and general formula about the expectation value of A. Now, when I say that you can predict the outcome of any experiment, I have to qualify what I mean by that. If we're talking about a Stern-Gerlach experiment, for example, and you have a silver atom that comes along and it either goes up or down, does one or the other, neither quantum mechanics nor anything else in the universe can tell you which way that silver atom is going to go before it does it. What quantum mechanics can do is give you the statistical distribution of a large number of such silver atoms passed through the same apparatus, all of which were prepared in the same way. And that's what we mean. That's what I mean by the predictions of quantum mechanics. Real experiments that are predicted by quantum mechanics. Experiments for which quantum mechanics can give an answer. Anyway, all such experiments, the outcomes of all such experiments are described by this formula here, meaning that if you know rho, then you can predict the outcome of any experiment. That's the significance of this formula. So the fact that these two rows are the same for these two ensembles means that they are physically indistinguishable to observer number two. Observer number two cannot tell which of these two apparently different ensembles he or she is dealing with.
So the trace gives the expectation value. Can you also extract the probability that it would collapse into individual?
Yes, you
states?
can. Yes, you can. This is elaborated on the notes a little bit. If you interpret the operator A broadly enough, you can get the probabilities as well as the eigenvalues. For example, if you replace A by the projection operator under one of the eigenstates, then it gives you the probability of ending up in that eigenstate. If you replace it by the projection operator multiplied by the p sub n times A itself, then you get the eigenvalue times the probability, and you can get that as well. So in fact, all the outcomes of all possible experiments can be determined by that formula that I gave you with a sufficiently broad interpretation of the operator A. Okay, so that's what we mean when we say it contains all the physics. By the way, I also say it contains nothing but the physics. And what I mean by that is that by making measurements on your ensemble, it's possible to determine what the density operator is. In that sense, you can measure the density operator. I can give you an example of that. In principle, at least. In fact, sometimes in practice, people actually do it. They certainly do it for the spin states of beams. This is commonly done. In any case, in this process of measuring the density operator, there are no phase conventions or any conventions of any type, such as of the type which occur when you're trying to determine what the wave function is. The wave function is only determined to within a phase, an overall phase, but there's no such convention. So that's a way of saying that when I say that the density operator contains only the physics, that's what I mean by it. All right. So in any case, the fact that these two density operators are the same means that there's no physical way for our second observer. I'm going to try to brighten this up a little bit. There's no physical way for our second observer to distinguish between these two apparently distinct ensembles. Excuse me a second. I'm going to turn on the light to make this appear better. Hopefully it'd be more easier to see.
Excuse me, I
Yes.
had a question.
Yes.
So you said that you can like directly measure the density operator. Are you like measuring a state that describes it, or like an eigenvalue of sorts that is like an observable, or can you explain that a
No,
little
what
bit?
you do is you compute expectation values of certain operators, and from that you can determine what the density operator is.
Okay, perfect, thank
That
you.
can be done. In particular, for a spin a half particle, you just measure the three components as expectation values, Sx, Sy, and Se, and this allows you to determine the density operator. The details of that are given in a section in the notes. I won't go over it in lecture, but it's an easy procedure. You can look at it and see.
Okay, thanks.
Okay. Now, and people really do this with real beams. I mean, real particle beams. Okay. Now then, I made it too bright. Let's see if I can dim it up again a little bit. Let's see, dim it down. There we go. Let me just lock it again. There we go. That's better. All right. All right. So now the fact that these, so I've got a little bit of a spiel to make here about the fact that these answers came out the same. This reveals by example, this reveals an important point, which is that if you have a given density operator, its decomposition into pure states and statistical weights is not unique. There's more than one way to do it. And this is a beautiful example of it. I could have also polarized them along the Y direction, plus and minus. I would have got the same answer. There's millions of ways of doing this for any given density operator. On the other hand, the fact that all the physics is determined by the density operator itself means that there is no way, there is no experiment you can do to determine what the quote unquote real wave functions are that lie behind the density operator. So there's a little bit of an attitude or psychological moral in this so what I'd like to do is to, if need be, is to give you an attitude adjustment about the density operator. So if you're like me, when you first encounter the density operator, what you say is, well, in the first place, this is obviously a mixture of classical statistics and these weights Fi combined with the quantum statistics and the pure states of psi I. That's kind of clear. And you might say, well, this is kind of a trivial grafting of classical statistics onto what's deeply profound quantum statistics in those pure states, or quantum measurement and so on, certainly non-trivial. And really all you've done is you just weighted the answers by the classical probabilities and just represent your ignorance of the state, right? That's the idea. Well, I think that's actually the wrong attitude, and there's a couple of ways of emphasizing or saying that. In the first place, if you're doing a real experiment like, Stern-Gerlach, for example, and you have a solar atom that went up and another one that went down, you cannot say, oh, that atom went up because of classical statistics and this one went down because of quantum statistics. You can't distinguish the two. All you can do is gather statistics of what the outcomes were and make measurements of that sort. Now, it is true by making such measurements, you can determine the density operator and thereby, as we'll see, find out whether the system is in a pure state or not. That can be done. But you can't attribute individual events to one type of statistics or another. Also, I think it's worthwhile remembering that like this ensemble, which is really essentially a thermal ensemble, could equally well be regarded as being a system in which every single silver atom is really polarized, but it's polarized in a direction that you just simply don't know what it is. You can't tell the difference between that and the system that comes from the oven. But more importantly, the fact that there is no unique way of identifying the quote unquote real wave functions that underlie a given density operator means that it's a mirage to try to look for those real wave functions. There are no real wave functions underneath the density operator, not if it's a mixed state. There's no way to define it. In fact, if you have a mixed state of a system, a quantum system, there is no wave function. And this is something to keep in mind if you want to think about the problem, let's say, of measuring the wave function. How do we know what the wave function is anyway, even when there is a wave function? Well, you might think about measuring it. It's worthwhile thinking about that. One of the things you realize is that you need, before you're going to talk about measuring the wave function, you better make sure you have a pure state, because otherwise you don't have a wave function. So those are all issues. So the attitude here, the best attitude to adopt is that the density operator is the fundamental quantity, and that the wave function is a derivative quantity, not primary. And that we ought to take the density operator as the central object which is used to express the postulates of quantum mechanics, and then take the special case of a pure state derived from that. And that's what I'm going to do before this lecture is out, is to show you how that works. But if we do take that point of view, then we need to kind of revise how we're presenting this material. Let's see if I can I'm losing track of my pages here. Yes, here, let me go back to this. Because a minute ago, I gave you these properties of the density operator. You find it here, which we quote unquote derive from our quote unquote earlier definition. Let's turn this around. Let's just say a density operator is any operator that satisfies these three properties. And let's go see if that works for a definition. Well, one of the things we'd like to know is if we have such an operator, is it possible, is it possible to decompose it into statistical weights and corresponding probabilities? And the answer is yes. You simply look at the eigenfunctions of the density operator. Let's write it in Ket language. Let's say rho acts on n and brings out an eigenvalue I'll call p sub n times n, like this. By the way, we know that rho has a discrete spectrum, not a continuous one, because operators with a continuous spectrum have an infinite trace, as you can easily see by just evaluating the trace of an operator with a continuous spectrum. The fact that the trace is 1 means that all the eigen states of the density operator are normalizable and discrete. If I then take this and sandwich both sides by n, like this, what I get is the eigenvalue p sub n, which is clearly non-negative because of expectation values of, because rho is a non-negative definite operator, because of property number 2, that this is greater than or equal to 0. Also, if I take the trace of rho, this is the sum of the diagonal elements of rho with respect to any basis. If I use the eigenbasis of rho itself, I can use any basis, but if I do, this becomes the sum on n of the p sub n's. But the trace of rho by property number 3 is equal to 1. And so you see the eigenvalues of the density operator can be interpreted as probabilities for pure states, which are the eigenstates of rho. Now, this doesn't mean that those eigenstates are quote unquote the real wave functions underlying the density operator. I think that's the wrong point of view. But what it does mean is that it's never wrong in working with density operators to assume that there do exist, even with a discrete set of probabilities that follow the formula we wrote down earlier. It's not wrong to do that. Anyway, that's the result of this little calculation here. All right, so then those then are the properties of rho kind of run backwards, except now we're taking the properties of rho as postulates of what a density operator is. Once we've done that, we now have the question of how do we know whether the rho is a pure state or not? Well, so we want a criterion for pureness, or maybe I should call it purity or something. I'm not sure what's the right word. Criterion for purity. Pureness is a better word. An obvious approach is, if you're given a density operator and you want to know it's pure, is just to diagonalize it. And if all the eigenvalues are equal to 0 except for one of them, which is equal to 1, then that rho is a pure state. And moreover, the psi, which is the corresponding pure state in the usual language, is the eigenvector or eigenstate corresponding to the eigenvalue plus 1, which it must be non-degenerate, by the way. So that's kind of a straightforward application of the definition. I'll give you some other theorems, though, that give you other criteria for whether rho is pure or not. So rho is pure if and only if, and by rho here I mean a density operator rho that satisfies the properties of a density operator. That's what's implied here. It's pure if and only if. I'll give you 3 criteria. One is that rho squared is equal to rho. The second criterion is that trace of rho squared is equal to 1. Recall that the trace of rho is always equal to 1. That's the normalization condition. But if trace of rho squared is also equal to 1, then it becomes a pure state. And the third one is that the entropy is equal to 0, where the entropy is the Boltzmann entropy, which I'll say something about in just a minute. In any case, these are three different criteria. So I won't prove these properties because actually they're fairly easy proofs, and I'll leave them as exercises for you to check that and to practice with understanding the properties of density operators.
Quick question, excuse me.
Yes.
Are those three, so am I to understand that theorem as rho is pure if and only if all three of those things are true, or that individually?
No, any of these.
Great, thanks.
If any of these are true, these are three different criteria and they're all equivalent. All right. By the way, rho squared equals rho means that rho is a projection operator. Obviously, psi outer product is a projection operator. Okay. Now, that's kind of an axiomatic approach, putting rho at the center of things, the density operator. A very important density operator in practice is the one that applies when you have a system in thermal equilibrium. Of course, when a system's in thermal equilibrium, we only have statistical knowledge about the state of the system. And in that case, there's a particular density operator that represents in quantum mechanics, our quantum knowledge of the state of the system. So the basic idea is you have a big heat bath here, a bath which is at some temperature T, and there's a usual thermodynamic parameter beta is 1/kT like this. And we have our system, which we can think of as being small here. And we place our system in contact with we have a means of producing identical copies of a given system. We place this system in contact with a heat reservoir, allow it to come to thermal equilibrium. Then in concept anyway, we then detach it from the heat reservoir and we make measurements on the system. And the outcomes of those measurements then are described by a certain density operator rho. And what is that? Well, the density operator rho for this particular case of thermal equilibrium is given by the following formula. It's e to the minus beta h divided by z, where z is the partition function. Now, h is the Hamiltonian for the system. Beta is 1/kT. E to the minus beta h is an example of a non-trivial function of an operator. And you'll recall back in the first lecture, I explained about functions of an operator. This is a non-trivial functions. This is an example where it gets used. So this is, it turns out, is the density operator appropriate in this case. I'm not going to prove this. In fact, I think proofs are tricky, but the discussion of that really belongs in a course in Stat Mech. But let me just say that this is a density operator which maximizes the entropy of the system under the constraint that the average value of the energy is fixed. Since I talked about entropy before, the entropy in general, this is the Boltzmann entropy now. The Boltzmann entropy is a functional of the density operator. It doesn't have to be this particular density operator, any density operator. The entropy is defined this way, is minus k times the expectation value of log rho, which is the same thing as minus k times the trace of rho times log rho. Again, the logarithm of an operator is another fine example of where you need to have a function of an operator, and it can be calculated in the ways that I explained previously. But in any case, this is Boltzmann's. This is basically, Boltzmann didn't know about quantum mechanics, but this is the obvious quantum generalization of the classical formula that he wrote down. I think it was quite early in the 1870s. He generalized the concept of entropy from equilibrium to non-equilibrium situations. All right. In any case, as I say, maximizing entropy subject to the constraint that the expectation value of energy is fixed leads to this density operator, which is the one used for the canonical ensemble and for systems in thermal equilibrium. Given the fact that trace of rho is equal to 1, but taking the traces of both sides, z is just a number here. It depends on the temperature parameter beta, but it's just a number. You get the result that z of beta is the trace of e to the minus beta h. E to the minus beta h is what I tend to call the Boltzmann operator. So it's the trace of the Boltzmann operator. If you take this trace in the energy eigenbasis, this becomes equal to the sum over the energy eigenstates of e to the minus beta en, where these are the eigenvalues. And this is, of course, a familiar formula for you from courses you've taken in Stat Mac. This is counting energy eigenvalues as distinct, even if they're degenerate. If you want to group degenerate values together, you'd need to multiply by Gn, which is the degeneracy of level n. And this is maybe the formula you're familiar with from Cattell's book or something. But in any case, the operator itself is given by the Boltzmann operator, e to the minus beta h. The partition function, of course, is important because it's not an operator, it's just a function, but it's a generating function of thermodynamic properties like the equation of state and things of that sort. All right. So that's what I want to say about density operators, everything except one final topic. And the final topic is that we need to revise the postulates of quantum mechanics to place density operators at the center of them and at the center of the logical structure. And so I've done that here and I've listed them out. And I'll go over them now with you. Several of the postulates are not changed from the way we saw them before. The earlier version of the postulates, I'll remind you, involved the notion of a pure state, which is undefined. And here at this point, everything we're talking about is now well defined. So postulate number one is the same as before, is that every physical system is associated with a Hilbert space. Second postulate is different. The state of the system is specified by a Hermitian non-negative definite unit trace operator, which we call rho, or we denote by rho, and which we call the density operator. Third postulate hasn't changed. Every measurement process is associated with a Hermitian operator A. The fourth postulate didn't change either. The outcome of a measurement of A is one of the eigenvalues of A, either the discrete ones or the continuous ones. The fifth postulate concerns the probabilities of measurements. The probability that A is equal to AN is given by the trace of rho times the projection operator onto the nth eigenstate of A. That's in the discrete case. In the continuous case, the probability that A lies on an interval between lowercase a1 and a2, this is the interval I down here, is given by the trace of rho times the projection operator p sub I onto that interval. And then finally, there's the collapse hypothesis, or collapse postulate rather, which in the case of pure states, you'll remember what it was. Basically, the state got replaced by its projection onto the corresponding eigenspace. And I'm going to leave it as an extra AFY means exercise for you to work out what the generalization of the collapse postulate is in the case of density operators. All right, that's all I want to say about density operators, at least in lecture. Are there any questions about it before we go on to another topic? Density operators are really the place to start in the measurement theory of quantum mechanics, not wave functions. And one of the things that's come out of this, I hope you understand, is that in general, for a general system, general state of a system, there is no wave function. Kind of dethroned wave functions here. Okay, if not, I'm going to move on to the next topic, which concerns the spatial degrees of freedom. We talked about spin so far, but we haven't done spatial degrees of freedom. That's what we'll take up now. Let's talk about the spatial degrees of freedom for a particle that moves in one dimension for simplicity here. So there's an x-axis here and an origin here somewhere like that. And by the postulates of quantum mechanics, there is a Hilbert space E, which I'll write E sub state here to indicate that it's the space of states of the system. It's what we call the state space. And I'm going to make some physical assumptions here. According to the postulates of quantum mechanics, the measurement of the position of the particle corresponds to an operator I'll call x hat, which acts on the state space of the system. And the eigenvalues of that operator are the possible results of measurement. I will assume that the results of measurement are continuous and range from minus infinity to plus infinity, which tells us that the spectrum of the operator x hat is the same. It's the entire real axis minus infinity to plus infinity. This is a continuous spectrum, and it means, therefore, that the normalization of the eigenstates of x have to be taken in the continuum sense. I'm going to make another assumption too, which is to say the collection of operators consisting of x hat by itself, just one operator, is by itself a complete set of commuting observables. That would mean that if we found an eigenstate of x, that there's in effect no way to resolve any degeneracies. In practice, what this means is that the particle doesn't have spin or other internal degrees of freedom that you could use to resolve the degeneracies. If it were a spin a half particle, you could measure X and then you could measure spin up and spin down and split it, you see. So let's assume in effect this is a spinless particle. All right, so these are various assumptions that we can make here. If that's the case, then it means the eigenstates of X are non-degenerate, so I can just write them this way with the eigenvalue. X hat operator acting on it brings out the eigenvalue like this. In this notation, the hat is used here to distinguish an operator, what Dirac called a Q number, from the X, which is the eigenvalue, an ordinary number, which Dirac called a C number. That's the notation here. The X with a ket in it, the ket with the X in it means the state vector, the eigenvector of the operator X hat with eigenvalue X without the hat. The eigenvectors are labeled by the eigenvalues. All right, so that's the meaning of that equation. Given that the spectrum is continuous, it means that we can only normalize these states X in a continuum sense. So the scalar product of XX prime can be normalized. It isn't automatically this way, but it can be done. You can normalize it to make it a Dirac delta function like this, and we will assume that this is true. Also, given that X by itself is a complete set, it means that we have a resolution of the identity, which is 1 is the integral over all X of the outer product of X with itself. When I write an integral like this without limits, I'm just being lazy. I always mean limits from plus infinity to minus infinity. If I don't mean that, I'll put the limits in explicitly. But in any case, this is the resolution of the identity. Also, the postulates of quantum mechanics tell us that the probability of measuring X on an interval, which is what we have to talk about since the spectrum is continuous, let's say the interval is X0 to X1 like this, tells us that this probability is the what does it tell us? It tells us this is the trace. Excuse me. I'm jumping ahead of myself. Let's suppose that we're dealing with a pure state. I've just been through half a lecture talking about density operators, but let's, in developing the properties of spatial degrees of freedom, let's, to be specific, suppose we are dealing with a pure state of this system. Let's call it psi. Then the postulates of quantum mechanics tell us that this probability of measuring X on this interval is just given by psi sandwiched around the corresponding projection operator for that interval. But if I write that out, the p sub I explicitly, this becomes an integral over dx between limits x0 and x1 of psi scalar product with x scalar product with psi like this. There's no zero there. That's just psi x psi like so. All right, so that's our probability. Now this leads to an important definition, which is of the wave function. We define the wave function psi of x to be equal to the scalar product of x with psi, where psi is the state vector. So this scalar product is taken inside this state space. And if I make this definition, then this integral, which I've just written, becomes an integral from x0 to x1 dx of the absolute value of psi of x squared. And since that's this probability, what you see is the absolute value of psi of x has to be interpreted as a probability density. It's the only thing it can be, since the interval I here was arbitrary. And of course, what we're doing here is reproducing familiar results from one-dimensional wave mechanics, starting from the postulates of quantum mechanics. This is the quote unquote derivation or pseudo derivation of the formalism of wave functions, starting from the postulates of quantum mechanics, which I promised in an earlier lecture. Okay. We have this state space here, which I just talked about, in which the state vector psi belongs. What's emerging now is another Hilbert space, which I'll call EWP, which is a space of wave packets. We've got wave functions. And we've got a wave function psi of x that lives in that space. There's a mapping between these spaces, and it's given by this formula up here. This formula tells us that if we know the state vector psi, we can find the wave function by taking this scalar product. That allows us to go in this direction. You can go the other direction too. These two spaces are isomorphic with one another. To go the other direction, we take the state vector psi, and I simply multiply it by the resolution of the identity, which is up here. Let me box it so I draw your attention to it. If I multiply both sides by 1, I can write the right-hand side as integral dx of x outer product like this with psi. And this can also be written as integral dx of x, the state vector, the ket vector x multiplied times psi of x. And just to repeat this, this is the ket psi, and I'll box this. Because what this equation then tells you how to do is to say, if I have knowledge of the wave function, I can then map back to this abstract state vector as I say, I can go the other direction here in this correspondence between these two spaces. Okay, so these are the rules for switching. If you like, this is switching back and forth between ket language and wave function language, but I prefer to think about this in terms of two different Hilbert spaces. By the way, what this formula shows you here is that the wave function is nothing but the expansion coefficients of the state vector with respect to the position eigenbasis. And more generally, that's what a wave function is. A wave function is nothing but the expansion coefficients of the state vector of the system with respect to some chosen basis. The bases that we commonly choose in quantum mechanics are associated, they're eigenfunctions of physical observables. Typically, they have to be commuting sets of physical observables. So we can talk about different representations, position, momentum, and so on, and there's others as well that are associated with physical observables. But there's nothing in the structure of quantum mechanics that requires a basis to be an eigenbasis of physical observables. You could use wave packets, wavelets, or who knows what all, and you can do those as well. And then you can talk about wave functions with respect to those bases. So in any case, this is basically what a wave function is. I'm again, in a certain way, I'm trying to dethrone wave functions from their central role as they were probably presented in first courses in quantum mechanics and making them kind of secondary here to this development. All right, so this is the way of transforming back and forth. We also have operators that act on the state space. For example, there's the operator x hat. We've seen this already, acts in the state space. Question arises, if x hat acts on a vector psi, what does it do to the corresponding wave function psi of x? Let's phrase this way. Let me write a state vector phi is equal to x hat on psi. And let's ask, what is the relationship of phi of x versus psi of x? Question mark, what is this relationship? Well, this is easy to establish because phi of x is, by the definition of a wave function, is a scalar product of x with phi, state vectors. And that's the same thing because phi is x hat on psi. This is x on the left, x hat in the middle, and psi on the right. We now let this x hat act to the left on an eigenstate of itself. This brings out the eigenvalue x. And what's left over is x times psi. And that is then the same thing as x multiplied times psi of x. And so what you see then is that the answer is that x hat in the state space corresponds to multiplication by x in the space of wave functions. Again, a familiar result, but deriving this from this formalism that we're working through. All right. So this is some of the basics of setting up wave functions and the basic formalism of wave functions in one-dimensional problems. We can make this three-dimensional. If we go to 3 dimensions, the position is now a three-dimensional vector. We can write it as x vector, and I'll put a hat on it here that again means operator. This has 3 components, x hat 1, x hat 2, and x hat 3, which are the same thing as the x, y, and z components of the position vector. But the point is that this is what we call a vector operator. A vector operator is really what we call a vector operator is really a vector of operators. Each component is an operator in its own right. And we assume in this development that these 3 operators, the components of x, commute with one another. That is to say that we have a commutation relation, x high hat with xj hat is equal to 0. Now, we don't exactly have to assume that, because as I pointed out in an earlier lecture, a commutator, whether a commutator is a 0 or not, is in principle something that can be determined experimentally. In this case, it means, for example, if I measure the x coordinate of a particle and then the y coordinate, and then do it in the reverse order, that the statistics of measurements of following those 2 measurements doesn't depend on the order in which they were carried out. Now, it wouldn't be practical to verify that experimentally, and I think in any serious way. But the point is that in principle, it's an experimental matter to determine commutators. And so the fact that the different components of x commute with one another is something that has an impact on experiment. And in fact, there's almost no experiments that would work out right if this weren't true in the realm of non-relativistic quantum mechanics. So this isn't really an assumption. It's ultimately it's a physical statement. So it's a consequence of experiment. In any case, if we have this, if these operators commute, then by the simple theorems we talked about, they possess simultaneous eigenstates. And we can write formulas like this, like x vector hat acting on x vector is equal to x vector multiplying x vector. But when you write this down, you have to understand this is shorthand for 3 simultaneous eigenvalue, eigenfunction, or eigenket equations taken all at once. And so apart from this, most of the formulas I wrote down earlier for the 1D case carry over in an obvious way into 3 dimensions. These are just some simple remarks about how things change when we move to 3 dimensions. All right, are there any questions about that so far?
With that notation, the ket would be just one that you would apply each operator to. So you only have one ket there, but you have each operator as a
That's right.
vector.
That's right. There's only one ket. It's a simultaneous eigenket of all 3 operators. But
Okay.
there's 3 eigenvalue eigenket equations. That's quite right.
Got it.
Absolutely. All right. Now, so next I'd like to talk about translation operators. A little physical motivation. The physical motivation is that if you have an isolated system, this is certainly true in classical mechanics, but in quantum mechanics also. If you have an isolated system, then the energy of the system doesn't matter. It doesn't depend on where you place it. You can move it to the right or the left, you can move it around and it doesn't change the energy. This is actually related to Newton's original considerations about the impossibility of measuring any absolute frame of reference. And so they're really is the same issue. In classical mechanics, this is expressed formally by the fact that the Lagrangian for the system, for an isolated system, or the Hamiltonian, both, are invariant under translations of the x coordinate. Now, of course, not all systems are isolated. If I play a game of catch with you, throwing a ball at you, the ball is clearly not part of an isolated system because it's influenced by the Earth's gravitational field. And obviously its energy depends on its altitude. So motion, moving the ball up or down certainly changes its energy. But that's because the system is not isolated and it's interacting with the Earth's gravitational field. If we enlarge the system to include the Earth as well, and we took both the Earth and the ball and we translated both of them by the same amount, then the energy of the system does not change. So it's necessary that the system be isolated in order to create this, in order to realize this fact of independence of energy. Now, the fact that such isolated systems have an energy independent of their position or invariant under translation is closely connected with the law of conservation of momentum, which appeared already as Newton's third law in his Principia in the 17th century. This connection between symmetries and conservation laws is an example of a general relation, which is usually called Noether's theorem, and it applies both in classical and in quantum mechanics. And I'll tell you right now that this course is going to have a lot of emphasis on symmetry principles, symmetry and conservation laws. This can be one of the main themes of the course. And this is, in some senses, the beginning of that story. In any case, this is all motivation for thinking about translation operators, which ultimately we will see is connected with not only the definition of momentum, but also conservation of momentum in systems, isolated systems in which momentum actually is conserved. All right, so let's talk about translations and translation operators. Let's go back to a one-dimensional quantum system and let's talk about a translation operator denoted by T of A, where A is a displacement that carries out the translation. We'll define the translation operator in the following way. We'll define T of A by allowing it to act on the eigenket x of position and require that the answer be given by the eigenket of the translated position x plus A. This makes sense physically because if we have a system that's isolated, if we have a system that's localized in the neighborhood of a point x, and you apply translation operator to it, then it's logical it should be localized at the translated point x plus A. This, by the way, is what's called the active point of view of symmetry operations. The active point of view is one in which the symmetry operator actually takes your system or the state of the system and maps it into a new state corresponding to the action of the operation. This is in contrast to the passive point of view, which is used in a lot of books, including most books on classical mechanics. In the passive point of view, what you do is you just have one system, but you look at it from two different coordinate systems. The trend in modern theoretical thinking, both in physics and in mathematics, is to take the active point of view because it's more amenable to an abstract treatment. It's less chained to coordinates. That's the point. Coordinates are something that, in general, it's a good idea to avoid if you can. All right. So we don't need to talk about a coordinate system here. We talk about translating the system. Well, there's a coordinate X, but there's only one coordinate system. There's not two. That's the point here. All right, in any case, this is the definition of T of A, identifying this as a translation operator in the active interpretation. Now then, and it's a reasonable definition. Now, the next question. So now let me list the properties of the translation operators that follow from this definition. The first one is fairly trivial. If the displacement parameter is equal to 0, then the translation operator is just the identity. That follows from just looking at it. If A is 0, you just reproduces X. Oh, by the way, I should mention that this formula, of course, just gives the action of the translation operator on the basis cats. But given that an arbitrary state can be represented as a linear combination of those basis cats by linear superposition, and the assumption that T is a linear operator, it implies that this T of A is actually defined for all possible states, not just the basis states. So T is now a well-defined linear operator by means of this equation. So in particular, T of 0 is equal to 1, which is a fairly simple property. Another simple property is that if you multiply two translation operators with displacements A and B, that you just get the displacement for the sum of the two. And since the sum of the two the sum of the displacements doesn't depend on the order, it means multiplying the operators doesn't depend on the order either. And what this means is that the T of A, the T operator, translation operators are commutative. Third property, which follows from the second and the first property, is that T of A inverse is equal to T of minus A. Just follows from adding up A plus minus A is equal to 0, which gives you the identity. So translation operators always have an inverse. And the fourth property is that T of A inverse is equal to T of A dagger, which is a way of saying that the translation operators are unitary. Taken together, these four properties of the translation operators means that the set of translation operators forms in a abelian group a group of unitary operators that implement the effect of translations on a quantum system. The word abelian is used in group theory to mean that the group operations commute with one another, and that's property 2 here. That's all it means. It just means commutative. So it's a commutative set of operations, but 1, 2, and 3 basically satisfy the group postulates, and item number 4 just says that the operators are also unitary. All right. Now I think all of these properties 1, 2, and 3 are obvious from the definition, and as for number 4, I'll postpone it for a while and we'll come back to it in a minute. But first I want to explore some of the other properties of the translation operators. The next question I'd like to pose is that this definition tells what T does to basis cats. What does it do to a wave function? So let's suppose I've got a state psi and I have another state phi, which is equal to T of A acting on psi. Then again, the question is, what's the relationship between the wave function phi of x versus the original wave function psi of x? Question mark, what is this relation? Well, we can work this out by just using our formulas here. Phi of x, let's make the wave function. Phi of x is given by the scalar product x with phi. And that's given by the scalar product of x times T of A in the middle and then psi on the right by the definition up here of what phi is. And that in turn allow me to insert a resolution of the identity between the T of A and the psi. So this becomes an integral over x prime of x T of A x prime like this times x prime psi, like so. Now then the x prime psi is the wave function psi evaluated at x prime. This matrix element of the translation operator, we can allow the T of A to act on x prime according to the definition up above. That gives us a matrix element X scalar product with X prime plus A. And that's given by direct delta function of X minus X prime minus A, like so. And so you can put this delta function in there in the psi of X prime and do the integral. It's easy to do because of the delta function. And what you get is psi of X minus A. Because X prime is equal to 0, or excuse me, the argument of the delta function is equal to 0 when X prime is equal to X minus A. That's where this came from. All right. So to answer the question then about what does the translation operator do to wave functions, let's remind us what it does to cats, basis cats. What it does to wave functions is this: is a T of A acting on psi evaluated at X is equal to psi of X minus A. And what you see is that there's perhaps a confusing change in sign here. The plus sign is obviously necessary here for the active interpretation, but this minus sign is confusing. Why is there a minus sign there? Why does T of psi end up giving a psi minus A? If you draw a picture, you can see why this is so. Let's make an x-axis here. Let's draw some wave function like this. And let's say this is psi of X. Here's psi of X. And let's pick some point here. Let's call it X0 and this psi of X. Now then, if I want to map this under T of A into a new wave function, and I want it to be an active sense, the new wave function has to be sort of rigidly moved over. That's what you need like this. This has got to be my phi of X over here. If I take this corresponding point X, the point on this curve that corresponded to X0 there, this has coordinate X0 plus A. Just obvious in the picture, moving the thing forward. T of A moves it forward, it doesn't move it backwards. Well, this means that phi evaluated at X0 plus A is equal to psi evaluated at X0. But X0 is just a dummy variable here. So if I replace X0 by X0 minus A, what I get is phi of X0 is equal to psi of X0 minus A. And this is the formula up here you see that I derived in a different manner. So this picture here just shows you that this formula for how wave functions transform under translation operators makes sense. It's what you actually need to move the wave function forward in an active sense. All right. So those are some of the properties of the translation operator. All right. Now, when we deal with symmetry operators, and this is true for at least all the continuous symmetries, of which translations is a simple one, there's particular attention attached to symmetry operations, what we call infinitesimal symmetry operations, one for which the parameter is small. And so let's look at T of A in the case in which the displacement is small. You can see that what this does to a wave function, if I sketch my wave function again, here's the original wave function. If T of A is small, then the new wave function is only displaced a little bit. You can sketch it here like so, and it comes down like this. And so you can see that the T of A is kind of comparing a wave function to a slightly displaced wave function. So it's related in some sense to the derivative of the wave function. I think it's clear from the picture here. We'll see that. But in any case, let's suppose that A is small. Now, first of all, here's a philosophical point. The reason that when we have symmetry operators, continuous symmetries, the reason why we're particularly interested in in infinitesimal symmetry operations, those that are close to the identity, that's what we mean by an infinitesimal operation. The reason we're interested in that is that symmetry operations of a finite displacement or rotation or whatever, finite parameters, can be built up as products of infinitesimal operations. So for example, if you want to move a meter, you can move a millimeter 1,000 times. That's the idea. And if you understand what happens on moving a millimeter, it gives you insight in what happens by composition and what happens on larger displacements. So there's particular attention devoted to what happens with infinitesimal displacement. So let's look at this in the case of translation operators when A is small. Let's do a formal Taylor series expansion of this operator in powers of A. I'll write it as A here, and then the first correction term is dt of A, dt dA, let's say evaluated at 0, plus higher order terms like this. This is expanding out to first order. Now the T of 0 is equal to the identity. That's one of the properties of the translation operators. As far as the dTdA evaluated at 0, T itself depended on a parameter. It's really a family of operators. But when I take the derivative and evaluate it at 0, it no longer depends on a parameter. And so it's just a fixed operator. So let's develop a notation for that. Let's make a definition here. Let's define an operator I'll call K, which is equal to I times dt dA evaluated at A equals 0, like this. And I'm going to put a hat on the K operator to distinguish it from C numbers K, which may appear later on. I use the hat to distinguish operators from corresponding C numbers when there's danger of confusion. If you wanted me to be completely pedantic about it, I could run around and put hats on all my operators, but I mostly won't do that in cases where it's not necessary, because capital T is understood to be an operator. In any case, if that's all right with you, I'll put the hat on the K here, make this definition. Anyway, with that, that's just a definition. If we do this, then when A is small, T of A is given by 1 minus I times A times K hat plus higher order terms like so, all right? So this is a result for what happens with an infinitesimal displacement. All right. Now, it turns out that this operator K hat is Hermitian. This, by the way, is why I split the factor of I off of it in this definition, was to make K Hermitian. How do I know that? I know that because T of A is unitary. I realize I forgot to prove that T of A is unitary. So let me put this on hold. Let's go back to that. Proof that T of A is unitary. So let's do it here on another page. The T of A is unitary was the fourth property. How do I know that T of A is unitary? Well, it works like this. T of A acting on a wave function, we just showed this, of x is equal to psi of x minus a. Let's just call this phi of x, meaning the new wave function. If I take the integral over x of phi of x squared, which of course is the scalar product of phi with itself, this is the integral over x of psi evaluated at x minus a quantity squared. But if I do a change of variable, writing x prime is equal to x minus a, and put it in this integral, and then drop the primes, dx prime is equal to dx, then this becomes the integral of dx of psi squared. And so the integral of phi squared is the integral of psi squared, and that means that the norm of the wave function is preserved by the translation operator. That's obvious in what it does to the wave functions. It's obvious these two wave functions have the same square. All right. Now, so in other words, the translation operator preserves the scalar product. It actually preserves the scalar product not just between wave function with itself, but even between pairs of wave functions which are allowed to be different. That actually follows from this result.
Professor?
Yes.
I was just sort of curious, like, is this sort of notion of hermiticity for T affected by this approximation with its Taylor series expansion?
No, I'm not. No, I'm driving. What I'm driving at here is that T is not a Hermitian. T is unitary.
Sorry. So yeah.
So I'm trying to prove that T is unitary, and then that will then be used to show that K is Hermitian.
Okay.
So, but the point right now is to prove that T is unitary. So we've got the preserved scalar products. Now, in finite dimensions, if I have, let's say, an operator, let me call it U, which maps an old psi into a new psi. If it's true that psi prime psi is equal to psi psi, that is to say that the scalar product is preserved under finite dimensions, the scalar product is preserved for all state psi, then this implies that U is unitary. And this is actually a simple proof, which I'll leave as an exercise for you. In infinite dimensions, this is not necessarily true, but it is true if it's still true if the operator Still true if the operator has an inverse. Has an inverse. And the operator T of A does have an inverse because it's T of minus A. And so the fact that T preserves the scalar product, if you're sloppy and just working in finite dimensions, a lot of books would just leave it at that and say that proves it's unitary, but actually you really need to show that it has an inverse. But in any case, this preservation of the scalar product means that T is unitary. So to go back then, given that T is unitary, and by the way, that's the proof of the fourth of the properties that I listed for the translation operators. That means that T of A dagger is equal to 1 plus I A K hat dagger. And that's got to equal to T of A inverse, which is given by just changing the sign on this, which is 1 plus I A K hat without the dagger. So if these two are equal, because T is unitary, you see this implies that K is equal to K dagger. So this correction operator in the Taylor series expansion of the translation operator, after I split off the I, is Hermitian. And this is significant because we like Hermitian operators in quantum mechanics because they correspond to observables. And that means that presumably this K here, which we call, by the way, we call this the generator of translations, is presumably connected with some physical observable with a physical interpretation. We'll see what that is in a minute. This is this K operator which emerges from the first term of the translation operator. Now, this expansion that I carried out here was only carried to lowest order, and it's only valid when A is small. What do we do if the displacement is not small? Well, here's some things you can do. If the displacement is not small, let's say A is not small, then let's choose a number n which is large. And then let's take T of A, and let's note that it can be written as T of A divided by n raised to the nth power. Because multiplying translation operators means you just add the displacement, so they'll all add up to A. Again, this is doing a meter is 1,000 millimeters. If we make n big enough, then A over n can be made as small as we like. And so then we can approximate that for a small value of A over n by 1 minus I A over n times K hat, like so, raised to the nth power. And this makes it plausible that the limit as n goes to infinity of 1 minus A over n excuse me, let's do it this way. This makes it plausible that T of A is equal to the limit as n goes to infinity of simply this thing 1 minus I A K hat over n raised to the nth power. Now, this formula, I like this formula because it corresponds to a picture that you can have in your mind of creating a finite translation as a product of a large number of infinitesimal translations. That's exactly the idea of this. There is, however, a limit of elementary calculus. You may have done it in your calculus course. The limit as n goes to infinity of 1 plus x over n raised to the nth power has the same structure as this formula here, except x is just a number and not an operator now. But this limit can be evaluated by L'Hopital's rule and so on, and it turns into e to the x. And it turns out the analogous limit also works for operators. And so this thing turns into e to the minus IA times k hat. So let me gather this in one spot, is that T of A is equal to e to the minus IA times k hat. And this is the exponential version of the translation operator in terms of k hat, which is what we call its generator. If I write out the power series here, it becomes 1 minus a k hat minus a squared over 2 times k hat squared, and so on. I can keep on going as far as I want. The k hat operator, you'll recall, was defined from the first derivative of t, But what this series shows you is that all the higher order terms are determined by that one operator, k hat alone. You don't need to invent new operators for all the different powers. Just one does it. And in fact, it's nothing but an exponential series. So this is a type of formula which is typical for symmetry operators. It's expressing a finite symmetry operator in terms of an exponential of what we call the generator of the operator. Yes, was there a question?
Yeah, sorry, I guess I'm still just like somewhat, maybe a little bit bothered by the fact that we just sort of take the first term of this Taylor series and it just happens to be like conveniently looks like the form of e to the I stuff when we, use this sort of a over n to the n sort of notion of like making a small infinitesimal step. And
Yeah,
so
so
like couldn't we have just like started out by just expanding T of A completely in its Taylor series and have noted that like that it's basically an exponential, like because you end up getting these like higher powers.
Yeah, but then you'd have to evaluate the coefficients of all the higher powers and show they can be expressed in terms of k. And if you do that, you're kind of missing the point that what I like about this derivation, as I said, is that it coincides with a mental picture of building up a finite operation out of a large number of infinitesimal operations. That's what this raising to the nth power is.
Right.
Now I can give you another derivation of this involving a solution of a differential equation, and you may like it better. I'm not going to go over it because it's in the notes, and I'm out of time anyway, almost. But if you want to take a look at that, and you can see this as a solution of a system of differential equations. It's basically a power series solution. It's very similar to the homework problem that you did for the first week's homework.
Got it. Yeah,
Okay.
thanks.
All right, so this is the exponential version then of the translation operator. Now, I think so. Let me just. I have 1 minute left. Let me deal with one more topic, and that is let's see what the operator k hat. This interesting Hermitian operator which is appearing here. What does it do to wave functions? So let's say in ket language, I've got a new state phi is given by k hat on psi. Again, let's ask what's the relation between the corresponding wave functions? But we'll analyze it in the same way. Phi of x is scalar product x with phi. But that's the same thing with x with k hat with psi like this. And that's the same thing as DDA evaluated at a equals 0 of x. There's an I in here. An I in here has to appear in here. X of T of A, psi like so. All right. But that's the same thing as DDA evaluated at a equals 0 times I times x, and then well, x T of A psi is the wave function of the translated state T of A psi. We worked out what that is. That's psi of x minus a. That's what this whole thing is. It's equal to psi of x minus a. So now doing this derivative, differentiating with respect to a, there's a minus sign from the chain rule. It becomes minus I times psi prime evaluated at x minus a, except we have to set a equals to 0. And this becomes in minus I times ddx acting on psi of x. And so what we see is that k hat as an operator corresponds in wave function language to the wave function here is language equivalent to this is that phi of x is equal to minus I ddx acting on psi of x. And I think you can see here the appearance of something that looks like the momentum operator. And this is where we're going to be going in the next lecture, is that this k hat, which is the generator of translations, is related to the momentum in quantum mechanics. And we'll talk about that next time.
Sorry, how did you go from the a derivative to the x derivative in the last line?
Just using the chain rule here, we're differentiating with respect to a, so it's just psi prime with a minus sign evaluated at x minus a. But you have to then evaluate that at a equals 0 because that's the rule here, and that just gets rid of the a. Psi prime is the same as dx d psi dx. That's all.
Okay, yeah, thank you.
All right. But see this minus sign that was in this, how the wave function transforms, that was necessary to get this minus to come out here. Okay, so that's all for tonight. Are there any questions then about the lecture? No questions. I'm going to stop screen share. I don't think I'll need that anymore. All right, one last call for any questions. If not, I'll stop the recording. All right, and here we go.